energetic, spend their entire operational lives exposed to the most brutal elements on Earth. From day one, they are explicitly engineered to survive freezing temperatures, searing heat, and direct physical impacts without shattering. This durability was the standard for the clean energy industry since the technology first took off. Engineers in the 1950s demonstrated that these modules could convert sunlight into electricity for decades without degrading. But that clock is now running out for the first major generation of solar infrastructure. We are currently looking at 27 million tons of out-of-date panels headed for the dumpster. And right now, roughly 80% of those end up buried in a landfill. Take a look at this exploded view of a standard panel to understand why we can't simply crush them up and recycle them. A panel is mostly tempered glass, along with about 5% silicon and a tiny sliver of highly valuable silver. But all of these components are permanently sealed together by a thick thermoplastic polymer. It's an industrial glue designed to be entirely water-resistant and completely impenetrable. That glue creates a severe economic bottleneck. Trashing a panel at the end of its life costs about $5. Properly recycling those fused materials costs up to $45 per unit. Solving this crisis requires a mechanical contradiction. We have to figure out how to unmake a machine that was built specifically so it would never break apart. A French startup called ROSI, tucked away in the Alps, is currently piloting a way to reverse engineer that indestructible seal. This diagram illustrates their first major step, a thermal treatment called pyrolysis. To eliminate the glue without destroying the delicate metals inside, they bake the panels in a custom 400-degree oven for up to 6 hours. Under that extreme heat, the solid plastic polymers vaporize into a gas. And here is the clever part. The thermal energy from the materials actually feeds back into the process. The modules themselves help heat up the oven, saving electricity during the bake. Turning plastic into gas obviously creates hazardous exhaust. To handle this, the fumes are forced through a 5-stage filtration system, ensuring that only CO2 and water vapor are released into the atmosphere. Even with that CO2 output, the math still favors the environment. Producing brand new silicon from raw materials releases between 8 and 12 tons of CO2 per ton of silicon. This thermal recycling method cuts that down to just 3 tons. Removing the polymer is the first essential step. Once that weatherproof tomb is gone, the valuable internal components are finally loose and accessible for the sorting phase. With the glue out of the way, basic mechanical sorting takes care of the bulk hardware. The heavy sheets of tempered glass, the aluminum frames, and the copper ribbons easily pull away from the pile. But the real target of this entire process is what's left behind, the raw photovoltaic cells, containing that 5% silicon and the 0.1% of precious silver. Separating these two elements requires a much lighter touch. The crushed cells are sent through a series of 5 to 8 connected chemical wet baths, deliberately formulated to avoid the harsh organic solvents or strong acids typically used in industrial extraction. Down at the microscopic level, the chemical baths trigger a physical release. You can see these tiny, hair-thin silver fingers, the very lines that conduct electricity in the panel, slowly detach from the silicon base. This chart tracks the final recovery yield from the entire process. By combining the thermal oven and the chemical baths, they recover 99% of the glass, aluminum, and copper. They save 95% of the silver and isolate the silicon at 99.99% purity. They take what would otherwise be toxic, permanently fused electronic waste and extract highly pure, marketable raw commodities. The underlying challenge here is economics. A single processed panel yields about $10 worth of recovered silver, and another $10 from the remaining glass, copper, and silicon. A $20 return means you have to process a staggering volume of trash to make the business survive. Scaling up from a 3,000-ton pilot to a 30,000-ton industrial site requires integrating operators and engineers with complex automation to keep costs low and the environment safe. To bridge the financial gap, governments have to step in. France, for example, relies on a mandated gate fee. Anyone selling or importing a solar panel pays into a fund up front, guaranteeing the recycling cost is covered decades before the panel actually dies. Even with the funding, the recovered materials have to find a buyer. Because modern solar technology requires silicon 1,000 times purer than the standard used 20 years ago, this recycled silicon is instead sold to the automotive, building, and electronics industries to help them lower their own raw material emissions. While companies work to perfect these recycling machines, researchers are trying to bypass the problem completely by redesigning the panels. Labs in the Netherlands are testing release encapsulants, polymers with a built-in trigger that unstick on command. In the US, researchers are experimenting with welding glass directly to glass, eliminating the need for plastic glue entirely. Dealing with the millions of tons of current waste requires clever thermal and chemical engineering, but ensuring the next generation of solar infrastructure doesn't end up in a landfill requires building a machine that plans for its